3v2, but our graph doesn't seem to make any sense. I don't know if that's like more of a MATLAB.
For which, for problem
3v2.
3b2. It's really more of a programming thing.
Yeah.
Generate data set that represents a monotone projection. The true variables manual, write the data set. Write a mathematical function. Label the data points. Plot to the separator. So that is, you found the linear discriminant function for the data that we provide?
Yeah. Or no, we
For your own data?
We made some data.
For your own two-dimensional data?
Yeah.
Right, okay.
And then we ran the find linear discriminant on the data set.
Yeah.
And then we plugged in the W vector and data vector, and then not the vector, data constant into the plot 2D separator. And then, yeah, our function seems off. So, yeah, I'm not sure how to confirm that our results from the previous are correct.
I think we're just poorly
you try
plotting in MATLAB.
Try plotting with some other tool that you're more familiar with?
I guess,
any other plotting tools?
Yeah, like R. But I think that, so I guess my question is, it seems like the simplest thing would be to just generate 2 points out of our, so we have a, I mean, we have a definition of a hyperplane, right? I guess it's a line since we're, you know. So we have the W and we have the theta. So what makes sense to me is to just like plug in an X and get a Y, and then plug in an X and get a Y, and then plot between them. But I'm not sure. So, but you need a. So W is a vector, right? So.
Do we use the first element of W as a quote?
I think so the vector going in, if I want to like just find X relative to Y, I would put in like 1, 0, and 0, 0 or something like that, or X, 0, 1.
I'm not terribly familiar with the MATLAB code, or actually MATLAB itself.
Okay.
So are you asking about a specific function in the provided MATLAB?
No, I'm just asking. I don't even want to ask the question I'm asking because
I'm sure that you can.
Trivial.
If you know W and it's degree 2,
right?
You can pull out individual elements, so you can solve.
So the first element,
right?
First element times X plus second element times Y. Is that what you meant?
I mean, you want to make Y the dependent variable,
right?
So I'm sure that you can solve that.
Well, but you have to have it to be in our thing. It's greater than or equal to some. It's an inequality, right? So that's where I get a little confused about like what value I'm going to pull out to like map.
So, but you want to plot the separator, right?
Yes.
So the separator is that equality is
0.
And so you can solve for Y.
Okay. Got it. It just wasn't all connected.
Like, can you do that already though?
No, we didn't. I could.
So let's see. Are there more? No. Well, I guess everybody liked it. So it either means that I solved everybody's problems last time, or
everyone thinks that they need to work on homework 1, and that this is going to be about something else, which would be my gambit.
Okay, we wouldn't do that to you, and what we would do to you though is that whatever we present here is important.
Yeah.
What color do we like today? Let's try dark green. So I'm not going to wait any longer. one of the classes of, did you have any other questions?
Yeah, a little bit about problem one.
Okay.
So I'm still trying to figure out a perfect algorithm. But like algorithm works on most trees, but it doesn't work sometimes. So
Well, but it is, your algorithm is
using the candidate elimination.
polynomial.
Yeah, it's
And
polynomial.
it's polynomial space, right?
Yeah,
Because you can't have polynomial time with exponential space.
yeah.
Okay. I can say you're free to go over the data in any polynomial number of passes if you want. In our answer, it is a linear number of passes, so it's not an n-squared algorithm, it's a linear algorithm. So
It's
go over the data.
n times m.
I'm sorry.
M is the number of data, and
N is the number of
n is
features.
the features.
Yeah. So, right, your algorithm will have to be at least nm because just to examine all of the data once.
Yeah.
Yes. But you can. I think that it still meets the requirements even if it's to some power. And obviously, like n squared, m squared.
Okay.
Though again, our solution is big O nm with some constant factor, which is the definition of big O. So yeah. So you know, maybe you can go over your data again a second time to confirm that what you did the first time was right, or something like that. Yes.
But is that, I mean, if you use so the falses tell you the most, right? They have the most information baked into them. Training examples that evaluate the false.
The negative one.
Right, the negative ones, I guess.
They both have information in them, and you need to look at both.
Actually, I don't figure out how to use the positive one.
Right.
I know that the negative one is useful to get a model, but positive one I can only use it to test it on the second.
Right, that's basically what we're at.
So you need to see if it'll be used at the stage where you're deciding whether there exists any consistent hypothesis. Any hypothesis is consistent with the data. So you will in the end use all of the data, one way or another. That's not necessarily all of it exactly as training.
So then what most of the proof then is about proving that, because if the question is how does it behave with the training data, and we've already gone over all of the training data, then doesn't that sort of all become trivial? And then what we're actually proving is that if we can actually confidently say that there is a hypothesis, or no?
You need to be able to.
Is that just really bad?
You need to be able to prove that at the end you haven't changed it some way that now it doesn't work in the previous training examples, and you need to prove that it's consistent with all the training examples, and then you should talk about under what situations it will give, whether it can give false positives or false negatives, and your algorithm sounds close enough to the answer that you'll either give only false positives or only false negatives. But there will be somewhere on it, if you think of a grid, 2x2 grid, some false answers that you will not be able to give. And the algorithm has sort of like a dual version, so I can't say exactly which one, but it depends on how you formulate it.
Mm.
So the point is you just need to prove that you're consistent with the data that you saw, and if you can prove that it will necessarily be consistent with the data that you saw, or it will tell you that there is no consistent. If there exists a consistent or multiple consistent hypotheses, that you get them. And then if none exists, that you'll find that and report that. All right, so more people have trickled in. Is anybody watching? Well, they can always see it. What I wanted to discuss, and I sort of built a little constructive thing here, is problem 3, and it felt to me like a lot of people were having trouble with problem 3 that arose earlier on with a difficulty with linear algebra, and just a difficulty with this sort of deluge of concepts all at once. So the question that I keep hearing is, how can we guarantee with these constraints that the separation will always between a point, some training example, and the separating hyperplane will be greater than or equal to 1. And so that's not necessarily obvious. So let's create some data that's linearly separable here. And the question is, the closest one here is going to have some space, and how do we know that that's always, or can always be greater than or equal to 1? Now, what I want to, so the way that I want to discuss that, and we'll get to that later, what I want to start with is that according to our definition of, is this the only board? Is it invisible thing? Let me try a different color. Make sure this is going to go on video too. Yeah. All right. Anyway, so we're gonna build to that. What I want to start with was that our definition of linear separability was that for positive examples, data is linearly separable. If and only if, for positive examples, the weight vector dot product with the feature vector plus theta is greater than or equal to 0. That's for y I plus 1. And the weight vector dot product features theta is less than 0, strictly less than 0. Yi equals not 0 but minus the negative examples. So to start with, given whatever hyperplane that we assume exists, there will be no negative examples on that hyperplane. It can come arbitrarily close to that hyperplane. So here's our separation boundary, and it's acceptable here for the positive examples to fall on that boundary because we had greater than or equal. But because the negative examples are strictly less than, there will always be some gap here. So the space that is the space within which the negative examples reside is an open set. And the space in which the positive examples reside is a closed set. And that's just an extension of the concept of an open interval or a closed interval on the number line to spatial topology. So This is like an open interval. It does not contain, it just means it does not contain that line. It contains anything arbitrarily close to that line, but not that line. And the closed set means that it contains everything arbitrarily close to and that line. Okay. So what this implies, and I just throw the topology vocabulary at you because it'll be useful to you sometime in your life. What this implies, of course, is that there's some space, let's call it epsilon, between the closest negative example and a separation boundary that works. So if we found this separation boundary that works, and we've found the closest negative example to that separation boundary, which defines our epsilon, we can always create a new separation boundary that is parallel to the original separation boundary, but it's 1/2 epsilon away. And by definition, it hasn't moved far enough to, this was the closest negative point. So it's not touching the closest negative point. It's no longer touching the positive points that were falling right on that separation boundary. So we've established, actually, what I almost want to do is I want to call this 2 epsilon. Let's call this 2 epsilon. It'll make things easier later. So we move 1 epsilon back into the middle of this little gap. It's 2 epsilon large. So okay, we've established that if this is true, then we can actually say that that's also true. Okay, that they're both strictly strict inequalities. Right? And so that's the first step, getting where we want to go. So the question that people keep having is why in equation number 3 for problem 3 is it going to come out to be greater than or equal to 1? I hope this is exceedingly obvious to all of you, but I'm going to talk about it anyway. If nothing else, then it'll be on the YouTube for those who do need it. So I want to give some. What I want to say is that there are actually multiple pairs of omega and theta that define the same hyperplane. Okay, and they define the same hyperplane, but they do something slightly different, which is let's imagine this in one and only one dimension. So if we see this in one and only one dimension, we have functions of the sort constant, and that's w. Write it as w even. We have functions of the sort w, which here is a scalar, times x plus theta equals 0, and these functions define single points. Okay? Yeah. But we can think of this as, we can also think of this as y equals wx plus theta. And if we do it that way, what we have is we have several. So this is a one-dimensional hyperplane. This point is a one-dimensional hyperplane. But this function that there are multiple possible functions with different slopes that will all pass through that that x-intercept that we chose. So for unique x-intercept, W and theta are not unique. Okay. And if we look at the value of this y here for this point, by altering, even with the same decision boundary, by altering the slope of these lines, we can alter the value of y for that point. Okay. So when we go into higher dimensional, yes.
I want to ask a doubt regarding this. So now you said that both these equations are for W1 and theta1. For multiple values of W1, theta1, W2, theta2, we can represent the same one-dimensional hyperplane, right?
Yeah.
But if we extend this concept to 3 dimensions, let's say 3 dimensions. So in 3 dimensions, a plane would be a hyperplane, a regular plane.
Well, yeah, it would be a regular plane, but
yeah, a normal plane would be a.
Well, point's a hyperplane, the line's a hyperplane, the plane's a hyperplane.
Correct, depending on the number of dimensions you take.
Yeah.
So now, if we change now for plane, the W would be the coefficients of x, y, and z, and theta would be the constant.
Yes.
But you will not have W1 and theta1 such that you get the same plane again. You will get planes that will intersect at the same line. So the only thing that can be the same is be different is W2 and W1. So theta will remain constant.
Because I feel like you're maybe expecting W to be an integer vector.
No, I can represent it as anything, but
because in a higher dimensional space, you can make W arbitrarily long or short, and compensate with theta to put the hyperplane where you want. W just needs to point in the direction of the hyperplane you want.
Correct. It has to be in the direction of the normal.
Yes,
so it can be 2 times, 3 times. You can multiply it by a scalar quantity and get whatever that you want. It will be the same. But if you change theta, the displacement changes, right? It changes.
Right. So you need to change W along with it. You can scale the length of W as you change theta, and you can have the same hyperplane. Well, I have an example. I'm going to get to an example in 2 dimensions, and I hope you'll see. But I just wanted to start in 1 dimension, because this is the idea that we're going to go to, and it's really hard to draw. You know, I can try to draw 3D on the board, and they can't go beyond that. But by starting in 1 dimension, I hope that you can see it clearly. Was what I was hoping. And
sorry, just to get back into your thought, the circles and the x's that you drew here are just showing that you still got your subspaces divided properly. Is that what they were?
So what I wanted to show is so this point is the point that is our decision boundary.
Right.
That's our hyperplane. It's that point.
Mm-hmm.
And this defines that point.
Yes.
That x. But there are, so for defining this decision boundary, there are other lines. This is cool. In the dimensionality of our problem +1, there are these other lines, and see our problem. The dimensionality of our problem is 1 here, but we have two fitting variables that we can alter. So there are multiple answers. And in general, the general way that we've written out hyperplanes and our decision boundaries is that we always have one more, counting theta as a dimension, we always have one more dimension than the dimensionality of the space we're trying to divide. So that's how I got here. What I said was if we wanted to define a function, and this function is exactly like this function equation 3, problem 3. We want to define a function that we want this to always be greater than 1 for every datum. Well, to start with, we've established that if there is a hyperplane, a separating hyperplane, there's a separating hyperplane where no datum falls right on the hyperplane. Okay? So we always have, at worst, a space of epsilon. Right? And now we can just set these coefficients such that that closest datum, epsilon, gets a y that is greater than 1. Does that make sense? We have, let's say we have a hyperplane that works, and then we can go in and say, what is the current minimum value of y on the closest datum, and then we can just scale w and compensate with theta until we get the slope that we want. Make that one amount to be 1 or greater. So I have worked. I did work up an example in 2 dimensions, just to make it exceedingly clear, as much to myself as to you. So in 2 dimensions, let's imagine we have the lines x plus y minus 1 equals 0, and graphing that. So that's 0, 1, 1, 0, 1, 1. That's going to pass through here. And our other option is 2x plus y, or plus 2y, sorry, minus 2 equals 0. Well, it's exactly the same hyperplane. So that also passes through here. But then when we come in and we want to evaluate at this point, just chosen for ease of calculation, this is the point 1, 1. Well, okay, so the first one we get 2 minus 1 equals 1. It's not on the hyperplane, right? So we did get that this distance is 1. And the other one we have 4 minus 2 equals 2. So for the other one now the distance is 2. And in general, we can multiply this whole thing by alpha, right? X plus y minus theta equals alpha 0. And so it's alpha 0 is always going to be 0, and any multiple of that hyperplane will be the same hyperplane. So does that, I hope that answers your earlier.
Yeah, I got confused because you're saying y is equal to mx plus c, right? And the slope kept changing in that. So the slope doesn't change, the slope remains constant.
So all I really want to say is that whatever w you choose, w just gives you a direction for the hyperplane. It's the normal, and you can move that hyperplane up and down with a different theta. But when you're evaluating a point to see what the value of the point is, you see this. Okay, it's not written here, but you see this this dot product, right? That's probably greater than or equal. Generalize this, right? So that dot product is. So here's the origin. Okay, and we have our normal vector, and we have some other vector to our datum. And as you know, of course, this dot product is like projecting and saying how much of this other vector exists in, or how much of it can be explained by that first vector. So this is, if this isn't a unit vector, this length scales with the length of W. So that can make it arbitrarily large or arbitrarily small. Anytime that you're actually looking for angles of things, often it is the case that when you really want to find just the angles, that you normalize and you force W to be unit length, but that's not what you're going to do in this assignment. We want to take advantage of the fact that you can make W arbitrarily long or short and still get the hyperplane that we want that's perpendicular to W by adjusting theta. And so I hope that that combined with the first proof makes it clear that if there exists a separating hyperplane, there exists a separating hyperplane that can be written with these constraints greater than or equals to 1 as in equation 3. So, does it or doesn't it? Just all nodding. Good. You look still a little bit frustrated.
No.
So.
No.
Okay. That's really all that I've worked up so far. So the rest is just you're going to barrage me with questions again. So get started. And yes.
For the question 3b1, can you give us an indication of what is inside D vector?
You want some explanation of how to do this? Or?
Yeah.
Okay. So it's a very fine balancing act to give help without revealing the answer. But I can go over the definition of linear programming again if you want, which is here earlier in the homework. You're allowed to you're allowed to do anything you want to create your matrix A and your vector B.
I have a doubt in what is inside the C cos.
Okay. I guess I can probably give you that. Or better yet, I'm going to try to lead you to coming up with it. So, would you like to come in front of everybody? And we're all friends here.
Yeah, I don't know.
So, the original definition of linear programming was that we have some C vector, obviously you recognize that we're going to multiply by some T vector,
yeah.
And we want that to maximize that dot product. So, so we wanted to max C times T such that A T greater than or equal to B. So that's the formal definition of linear programming. And over here, what we wanted was to minimize. Here, our objective is to minimize delta. So just expressions
We are given a data where we have samples like 1, something, and then the result. So this is our X.
So this is your
Y.
This. The sample might be right. So this is our X and this is our Y in this case. So can we write this sort of as a partition matrix? Okay.
So this is our X and this is our Y. And what is that in terms of A, B, and C?
So the problem is sort of the opposite. It's what is A, B, and C in terms of our data and the labels, and our functions. So here equations 3 and 4 are going to have to be encoded as A and B, and equation 2, well, A, B, and T will encode equations 3 and 4. And equation 2 is somehow encoded with C and T. So, minimize delta.
Okay, that's the function.
Yeah. So T is all of our optimization variables. T has to include everything that we can alter in our optimization to try to make our optimization come out right. And in the end, T will be our answer. So somehow you need to form a vector T that includes everything that we can alter. What are the things what are our optimization parameters? What are we trying to find? So any peanut gallery is not only free to, but encouraged to participate.
Are you talking about T at this point?
Yeah. Yeah. So this is the canonical form of linear programming.
Sure.
And yes, you're free to go. So let's see.
T should be the X of the data.
But it's also got more information.
And so our problem was min by varying delta, delta. But we're also, are we not also going to vary W and theta?
So T has W and then theta and then delta.
Right. But our minimization problem doesn't really care about the values of W and theta, but it is going to alter them in order to try to find the minimum delta. And so the vector C and the vector T are intimately linked. And I'm sure we all know the definition of the dot product. And so how can we, to start with, does anybody have a candidate for T? What's that? Yes, please hear it. Which one is? You were the only one that's had the hand.
So you just concatenate W with theta and delta.
Awesome. So we have W, theta, delta. It's one vector. This is all of W. And okay, so we want to make that dot product with C comes out to just be delta. So what's our C going to be?
Which is zeros and then a 1. In plus 1 zeros, I guess.
Yeah.
It is the number of the C.
Awesome. So now we have that are using that C and that T. We have our, is this max? This is min. This is min. Min and max are, of course, just a negative sign, and you'll have to look at the package that you're using to see which one it is. If it's min and if your objective is to min and your package does max, you're going to need to multiply C by -1. Just go backwards, but that's trivial. So then next was one we really can't give away, but I hope that you'll be thinking about it, such that yi well, to start with, though, what's I'm sure obvious is that the right-hand side has to be constants. The b vector here is constant. So the b, or a, b, and c are all constants. A, b, c are constants. So obviously we need somehow to pull the delta off to the left-hand side. Simply rewrite, of course. I plus delta greater than or equal to 1. Yeah. And then the rest is just that you need to find similar in approach to the way that we figured out how we were going to make what we were going to make t and what we were going to make c, and constrained by the fact that we've already chosen t, so it makes mostly similar to the way that we decided how to form c. We need to figure out how to form every line of A. Okay. And we need to make sure not to miss constraint number 4. Constraint number 4, which was the delta is greater than or equal to 0. And that's, I think, fairly simple. Because we've already established that C dot product of T is delta, right? So that's one line at the end, at the beginning, or really wherever you want in your matrix A that would be equal to C, and the corresponding B should be equal to 0. If it's of this form, then plus or minus, or times plus or minus 1. So really, all that's left at this point is to figure out how to encode this as a vector. And then you just stack all of those vectors into a matrix. What is a matrix vector operation? A matrix vector operation is nothing but so what is this? This is going to be T, B, A is absolutely nothing but B I equals A rho I, right? I everything dot product with T, right? You just this is a stack of vectors, and you go down each one of these vectors. Sorry.
You said corresponding B should be equal to 0.
You said what?
You said at one point the corresponding B should be equal to 0.
B?
The B corresponding to which should be
corresponding to this constraint. So you're going to need to. There are all of these constraints, which you have one for each datum. And then you must not forget this constraint, which is that delta is greater.
Can you come back to the lower bound?
I'm not sure I understand what you mean.
In the limit log function, there is an option to specify lower bound, right?
There is.
Yeah, there is an option to specify lower bound.
That's what is given in the appendix.
Because if you look at the appendix and if you take the T1 plus T6, I mean Ti greater than equal to 0, isn't that what will correspond to delta greater, not delta, but that would be one of the conditions there.
I think you're going to have to ask somebody that's more familiar with MATLAB than I am. If I understand this, I think what this is, maybe this is letting us
Set the lower bound.
give multiple A matrices.
Yeah.
I'm not sure. So somebody that's more familiar with MATLAB than I am maybe can answer that. But I'd really prefer to discuss it in canonical form, because if we can understand it in canonical form, and if you can get used to putting your problems into the canonical form, then it won't matter what package you use. Every package will be able to handle the canonical form. So in the canonical form, this constraint becomes just another row of our matrix. And as I was saying earlier, this is just each of these constraints is a vector that's going to get dot producted with RT, and we say that that should be greater than or equal to the corresponding B. So the only thing really that's left here is to figure out what these vectors need to be. And if you can figure out what they are for the two cases of a positive and negative training example, then you can build the it. And with here's already we've solved what B should be, except down here. So B is essentially solved for you. And I don't want to go to the point of just giving you the answer. So, but I hope that's helpful, at least, without cheating. Was there anything else?
Yeah. In 3D2. He asked for an interpretation of theta.
Data.
Yeah.
Right.
Like theta helps in forming the conjugate.
With the linear program.
Yeah. For in the conjunction case, where n equal to 10, you ask what theta denotes. So, I'm just asking, is there more to just theta being part of the conjunction? So, like if you have a conjunction of A and B, it's A plus B minus 2, right?
Well, I think it's going to be something along the lines of what I began
what do you
the
expect
section with. I think it's going to be along the lines of what I began the section with, which is a discussion of the intimate relationship between W, theta, separating hyperplane.
Just in the general case, not just with respect to conjunctions, is what he's saying.
Oh,
I mean, sorry to.
yeah. So, we're not expecting something for this particular example?
What we're expecting is that you're going to consider it deeply and scratch your head and be upset and bothered by it, and then write something that explains what you think. So, okay, we still have a few minutes, and I'll stay right to the wire, and then we'll move down to my office if anybody still wants to stay. So, are there any questions for the last 5 minutes here?
So in the place where we're trying to do the algorithm for learn patches, like that's B3.
Yeah.
So the first part is okay, but then at the end it says find one alphabet in position such that the linear separator computed from the resulting feature vector has a perfect accuracy for the training and imperfect for the test data set. Can any clue about how we can start doing about this? Like I have the image, but are we supposed to infer something from the image?
You have badges data set, right?
Yeah, there's an image that's created which has the features. The x-axis has the characters and the y-axis has the positions, and there's a weight standard. I can show you the image.
So, I mean, essentially it means to try each of the features, subsets of the features, but it says quite clearly, you just read it back to me, that there is one feature that is perfectly predictive. And so try all of the sets of one feature, and when you implement it fine linear discriminant, you're giving it the data set as your input is a data set as a matrix, right? So you can easily slice this matrix to give it just a few features, and the math's not going to change.
Yeah. But how do we kind of know what features to give?
Brute force search. If it says that there's one feature that is perfectly predictive, then there are a big O of n one feature sets, and I'm sure you can write a for loop.
Were you just talking about the forward point conjunctions?
The badges.
Oh, the badges.
So okay, I think that's it for this room. But I'm going to be down in my office, which is I guess a slightly more intimate setting or whatever you want to.